once in a while. But it had to be fairly quiet so everything could stay there and survive and didn't get just swept away. And we end up with what we call a fossiliferous limestone because it's mostly fossils. But those fossils are calcium carbonate. But they've become a sedimentary rock. Another one is this little thing. It's called coquina. You may have seen it in the making. Notice it's nothing but busted up little pieces of shell and cemented back together. And coquina forms right along the beach. You know how the wave goes up the beach and as far as it gets, and that's where it kind of leaves a little row of little shell fragments and wood and seaweed and all that stuff. That's where it accumulates. Well, that's what this stuff is. If I can bury that and preserve it and get it cemented back together, I've got coquina. Now, when a geologist finds coquina in the rock record, this is cool because right away it tells them a couple things. He says, you're standing on an old beach, and because it was right at the line formed by the waves, you know exactly which way the beach ran. This is really kind of a cool discovery. Coal is a sedimentary rock. It's the remains of plains, swamps that have been buried, compressed. Oxygen was kept from getting in there so it didn't just all rot away. It was kept in a reducing environment, oxygen-free environment, and that carbon material just got compressed together. And here you can see a sandstone with a layer of coal in it with another sandstone over it. So the trick here is to get these swamps buried quickly and seal them up so that the oxygen can't just rot all the vegetation away and decompose it. So what kind of environment can I do that? Well, I know the coal has to be a swampy area. Here I've got a couple of big, massive sandstone units, and we see this along the east coast of the United States today with the Barrier Island system. You've got the mainland, you've got a lagoon, and then you've got a big island. And these big barrier islands, the waves are basically causing them to migrate toward the mainland, and they migrate right over the lagoon areas. Perfect. You've got this lagoon, the swampy lagoon, you got the sandy barrier island burying it, and you just get kind of cycle after cycle of that, and the result is these kinds of coals. So one of the easiest things that you can do when you look for coals is go, okay, where are the old beach lines? Where are the old coastal zones in these rocks? And if you look at it, we've got different grades of coal. Peat is perhaps the least desirable. And here's a Pea Pod. You can see the guys just breaking it up with a big flat shovel. I mean, it still is just kind of the plant remains. You can still see twigs and leaves. You see it's still kind of swampy. And this used to be something that they'd break into blocks. They'd put it up on racks to let the water drain out, let it dry, and then they'd sell it for fuel. And a lot of the Irish peasants would use that back in the 16, 17, early 1800s. Pretty low heat quality. It's kind of, charcoal's about better than peat for the most part. Today, though, peat has a very noble use, and that's for roasting malt for single scotch, single malt scotch. And oftentimes, it's these different peats that give the scotches their different flavors during the roasting process. So, pretty cool. But pretty crummy for coal. Now, let's bury this a little bit, squeeze it together, get the water out of there, and we jump up to the next level of coal that we call lignite. Sometimes they call it brown coal, because you can still see a twig or two. It's kind of brownish in color. It hasn't really, gone that far. And it's good coal in the sense that we've got a lot of it. All of this coal here in the middle part of the country tends to be toward the lignite side of things. A lot of ash when you burn it, so the electric systems, the electric utilities that use it, have to have these big ash collectors on their smokestacks to catch the ash and dispose of it. But it's usually pretty cheap. You gotta mine a lot of it though. It's usually surface mine right near the area that you're gonna burn it in. Okay, bury that a little more, kind of start squishing those bits together a little more, and we go up to a low-grade coal called bituminous coal. And this is, for the most part, the coal that we burn in the United States today. Most of this is coming from the Rocky Mountain areas, Montana, out here, down in Colorado. That's the coal that tends to get burned in the Indiana, Ohio, Pennsylvania, New York electric utility plants. So this is the coal that we deal with when we're worried about acid rain and pollution in this area. This is the ultimate coal, anthracite coal. It's the coal that built the United States, essentially. It's a hard, dense coal. It almost looks like glass. It's so shiny. Here, it's been subjected to a lot of heat and pressure. And this is kind of where we draw the line now between the coals that are sedimentary rocks and this coal, anthracite, that now becomes a metamorphic rock. And it's this process that says these are coals that have been subjected to a lot of heat and pressure, mountain building processes. They're buried deep in the earth. They're in mountainous terrain. So these are typical of coals out here in the Appalachians. And they are deep. The mines are expensive and usually fairly dangerous. But that was the big coal of the 1800s. Now it's surface mines of bituminous out in the west that we're using. You can see this bulldozer here for scale on the thickness of this coal bed. But if I want anthracite, I'm underground in mines getting to it because it's buried deep in these mountain systems. That's where the heat and pressure was to make that a metamorphic rock. So you've just compressed everything essentially and made the carbon and the heat in a tighter arrangement.
Is that also where natural gas is derived from?
Some, yeah. In the process, you do make natural gas here. And this is a big danger in a lot of coal mines, is the natural gas that's given off by the coal forming process. And if you, mostly methane, it's obviously lethal if you breathe it, but it's also a big explosion issue. So this is something that they have to vent. In some areas, what they do is they actually drill wells from the surface into where they're going to mine. And they put in gas wells and pull the gas out and actually produce the gas for a few years. And then when it drops down to a level, then they go in and start mining the coal. So you can get both out of the same deal. Yeah. You know the old saying, the canary in the coal mine? This is the old-time safety device. You'd always, the miners, every shift would have a canary with them in a cage. And if the methane started to build up, canaries are very sensitive to that. And they'd just fall off their perch and, down on the bottom of the cage. So they'd have a miner kind of keep his eye on the canary. And if they saw that, they know the methane was building up and it was time to get out of there.
That hurt the canary?
Yeah, it usually killed them.
Oh, it kills them?
Yeah.
All right.
Yeah, he was the sacrificial canary. Yeah. But better to, bump off a canary than a whole shift of miners, right? Yeah, everything's relative. Okay, beautiful. Coal forms by cyclical sedimentation where swamps are rapidly covered with sediments. Seconds. 18, 19, 20. Okay. And everybody likes that answer. Okay. Yeah. The whole trick is you've got to keep the vegetation from decaying. So you've got to bury it fast. And that means you've got to have some kind of an environment of deposition. The things are going to happen pretty rapidly. And this idea of migration of barrier islands, well, it works pretty well. So and that's where you get some big deposits. You can do it in little swamps with, a little flood from a river or something, but oftentimes the deposits aren't big enough to make them economic. So you need something that's, indicative of an old coastline. Okay, so sedimentary depositional environments. That's kind of where we sum up a lot of this. And we're looking at things like river channels, lakes, beaches, that deep floor out in the basin, out in the ocean. We're looking at restricted basins where we have salt deposition, desert sand dunes, glaciers, swamps. All these places now are places that you can pretty much click into with the idea of an energy level. Swamps are pretty quiet, low energy areas. Beaches are pretty high energy with the waves crashing on them. So you can immediately look at the sediments, get an idea of the energy level, and start sorting out where this sediment might have accumulated to become a sedimentary rock. This is the cool thing about sedimentary rocks, is they give you the window into what was going on in the area geologically back in the time they were being formed. Cool. Okay, let's take a look at the windows. Here's our kind of summary diagram going from source land to streams down to beach, down into the deep basin. And we can kind of see that sorting's getting better, sizes are getting smaller, mineralogy's becoming the same. But there are going to be a few different spots along the way. Let's look at a river system. Here's our big processing system. Normally, it's just a nice river flowing along. It's got a floodplain, and then all of a sudden we've got a flood. Lots of water, real fast. The river's out of its bank, so it's out on the floodplain. The floodplain's kind of the extended channel in the way you can think of. And all of a sudden, as it's doing this, the old sediment that was laid down out there from the previous flood, some of it's starting to get ripped up. It's getting incorporated in the water. It's getting carried away. So I'm making a new unconformity here, aren't I? And eventually, the flood subsides, the water's back in its channel, but it leaves behind all this sediment now that it was carrying with it before. So I see kind of this lag of the ripped up material from the flood stage, and then I see this finer sand and clay from the waning stages as everything kind of calmed down at the end of the flood. But there's my surface, my new, what I call a bedding plane, because I've got a bed of sands from the previous floodplain down here, and I've got a bed of gravels and sands up here from the most recent flood. And it's pretty easy to pick out that erosional surface, that, in this case, a disconformity between the two events. So disconformities are very common on this scale. You don't have to have these global events to make disconformities. Here's a real example of one right here. Look at the disconformity right there. Here's all of the sands that were laid down as part of the floodplain previously. Here's the channel that cut into them, and here's the material that the latest flood carried along. That's pretty powerful. And look at the size difference, how this stuff, big boulders, a lot of material. Here you can see there's the surface right there. You can see the old floodplain deposits that have been cut through. You can see the new sediments that have been laid down in the new channel. That's the bedding plane right there. So right away, just looking at this, I know I'm out on a floodplain area, river system. Okay, so I put myself somewhere in this environment area. Well, what if I get to the coast? Sands on the beaches. I'd expect to see some pretty nice clean quartz aeronites there, wouldn't I? Or if it's a delta area where I see the sands and the muds just being dumped out into the basin, I expect to see some shales. I expect to see maybe a mix of sands and shales. And here I've got a barrier island, and it's being eroded on the front side. The sand's being carried back into the lagoon, burying it. This is a coal formation in the making. Eventually, as this barrier island buries this lagoon, that lagoon's going to become a new coal seam. One of the neat things I can kind of look for are the same structures that I see on the beach today. Ripple, the waves go back and forth. It's leaving little ridges and ripples out there in the sand. And I can tell a lot by the shape of the ripple. For instance, here I've got a current that's coming in. It erodes and picks up sand back here, and then when it gets up to the crest of the ripple, it drops the sand off in the lee where it's a little protected. So this ripple is building by kind of being cannibalized on the backside by erosion and new sand being dumped out. So this whole ripple's kind of moving along on the beach. Well, what's neat is when I get a ripple that's asymmetric like this, and that gets preserved as it gets buried and becomes sedimentary sandstone. And now I can see exactly how this beach grew. Because I can see these little slip faces, and I know that the beach was moving this way, and then maybe it was coming in this way. I can trace out each layer and tell exactly how that beach was formed. But sometimes I'm in areas where I've got tide. And, part of the time, the majority of the water is moving this way. The other part of the time, the majority is this way. So I've got kind of a back and forth motion of building these ripples. Some of the time, it's eroding on this side, depositing here. Other times, it's just the opposite. So now I don't get asymmetric ripples. I get these little cuspate symmetric ones instead. So now I know I'm in an area where I've got a tidal zone that's affecting what's going on in the beach. It's not just the beach waves like we'd see over at South Haven. So just looking at the shape of the ripple, I can figure out what was going on in that beach. And here you can see some really neat ripples, swim fin for scale here. And you can see how they're kind of asymmetric. They're kind of shallow on one side and steep on the other. So I can tell exactly that most of this was kind of being deposited from left to right. That was the way the water motion was going most of the time. Here you can see it in cross-section, bedding plane. You look at the growth of the ripple in this direction. So notice that down here, same kind of direction. Here, and something's going on. Not having quite as much success building ripples. And here, notice things start kind of moving the other way. So there was a shift in the orientation of this beach with the ocean. So with those things, I'm kind of looking down in this part of the system, aren't I? I'm looking a little higher energy. If I start seeing things like this, these fossiliferous limestones, or these neat little oolites, these are kind of neat little things that formed in the swash zone, or coral reef type of debris, I know I'm going to be offshore. I'm not going to be back here on the beach, but I'm going to be in a band paralleling the shore out in shallow water. So again, I've got a way of figuring it out. When I see widespread deposits of shale like this, I know I've got to be out in the deep basin. This isn't just a little swampy area off on the side of a river. I mean, you can see this just goes on and on and on. This was a big old basin out there, filling up with those silts. Kind of, seasonal basis with pulses, probably in the springtime, forming each of these little thin layers. This is over 2,000 feet thick. Paper thin layer at a time. One period of time. millions of years, right, guys?
Millions.
Yeah.
Millions. It's crazy, bro.
So now we're out here in the